right, working with the imaginary number I, we know that I is equal to the square root of -1. So if I was to square each side, I squared is equal to -1. We are in lesson 6-7. This is algebra 2. We're working with the imaginary number I, which I think is super fun. One of my favorite lessons. Our essential question is, can you use the number I to simplify square roots of negative numbers? So let's look at what we're talking about. I know that this negative can come out of the radical as I, and 32 can break down into 16 times 2. And I know that the perfect square of 16 is 4. So 4i root 2 is the same thing as the square root of -32. Now they're throwing in some adding and subtracting. We always want to take out our i's first. So I'm going to take out the I of the square root of 6. I have to break up the square root of -24, take the I out, and we have 4 and 6, where the perfect square of 4 is 2. I'm going to rewrite this so we could see 5i root 6 minus 2i root 6. We do have to have like terms to add this, and 5i root 6 and 2i root 6 are like terms, so we're going to subtract actually to give us 3i root 6. All right, when you multiply, it is very, very, very important to know that you always have to, and I know it sounds funny, we have to pull out our i's first. Because if we multiply a negative times a negative, it's going to be positive. So we have to make sure we pull out those i's. So we have I root 3 times, well, we could break this one up too, right? We can break this up to 9 and 3. So let's deal with what we know. We know I times I is I squared. I know the square root of 9 is 3. We're going to put that number in front of the i's. And root 3 times root 3 is root 9, which we know is also equal to 3. So we have to continue to multiply, and we get 9i squared. Oh wait, that I squared is a -1. 9 times -1 is -9. So the rule here to remember is to pull out your i's first. And we do also have to need to know how to rationalize. Let's pull out our i's first. I already heard the teacher say, pull out your i's. So we're going to do that first. Well, I need a pen. I have an I, and I know 18 breaks up to be 9 and 2. I have an I, and I know 12 is 4 and 3. Well, can't we reduce here? Let's make this a 2, and let's make this a 3. So I'm going to rewrite it all. I have 12i root 2, and then I have 2i root 3 in the denominator. So when I reduce this stuff, I know 2 goes into 12 6 times. The i's cancel out. But what can I not tab in the denominator? Good, I cannot have a root 3. So to get rid of that, I'm going to rationalize the denominator by multiplying by root 3 over root 3, because I can multiply anything through by 1 and not change its value. So I get 6 root 6. Well, root 3 times root 3 is root 9, which is 3. But I can continue to reduce, and I know this final answer, because 6 and 3 can reduce, is 2 root 6. Now, the whole reason we do this is for questions like example 7. So I am moving on to finish my lesson. Example 7, we're going to solve this just like you would. Your first gut of guts tells you to do what? Good, subtract 25 to each side. So 4x squared is equal to -48. And your gut of guts continues to tell you to solve by dividing by 4 to get the x squared alone, and we get -12. Now, to continue to solve, to get rid of a square root, I do have to square. What I do to one side, I do to the other, because that's going to cancel out my square root. And don't forget, when I solve for an x squared, I need a plus and a minus. And remember 12, I have root 4. Oops, this little negative can come out to be I. And 3. So my final answer, x is equal to plus or minus 2I root 3. Don't forget your plus or minus. And the whole reason we do this is typically if we look at quadratics, when I'm graphing a quadratic, which is a parabola, it typically hits through the x-axis. And this is why we call them zeros, or solutions, or roots, or x-intercepts. All of those are the same thing. We're these two numbers. But because sometimes I get an imaginary number like this, notice that on my Cartesian coordinate system, this graph hits up here. So it doesn't really have a solution because never, ever, ever is it touching this x-axis. The other one touched the x-axis, great. This one does not. So therefore, it doesn't really have a solution. It has what we call an imaginary solution. So the imaginary is the I, and we have these imaginary solutions where, hey, maybe it would have hit here and here if there was this imaginary x-axis.